So yeah, hi, I'm Rahul. So my project was on building a high voltage gallium nitride traction inverter for solar electric vehicles. And to introduce the project, I'm going to show you Helia, which is this vehicle that Cambridge University Eco Racing built in 2019. And Helia is a 4-seater passenger electric vehicle, has a range of 900 kilometers on a full charge, and most importantly, has a cruising power of just 2,500 watts at highway speeds of 80 kilometers per hour. And to put that in perspective, that's the power that your average electric kettle would consume. And peak power consumption, going up hills and accelerating would be around the ballpark of 12 kilowatts. So this is an incredibly low power, high efficiency vehicle. And in 2019, we raced Helia across Australia in the Bridgestone World Solar Challenge. This is a grueling 3,000 kilometer race across the Australian outback. And there are only 2 charging points in the middle of this whole journey. And that corresponds to about 1,200 kilometers between stages at max. And unfortunately, in the event, Helia had to withdraw before completing the first stage because of one of our inverters failing. But nevertheless, we managed to go almost 1,000 kilometers, which was an admirable result given that most vehicles entering did not even make it to the start line. But this did identify one major area of improvement, and that is the inverters. So the current inverters that we use in Helia are this one pictured here. It's called the Tritium Wave Sculptor 22. And there are sort of 3 main reasons why we want to change these and build something ourselves. First one is that the bus voltage of these inverters is limited to 160 volts, which in the scale of electric vehicles is relatively low. This introduces 2 main problems. Firstly, voltage sag. When the battery depletes to about 30%, our top speed then becomes limited to about 50 kilometers per hour, which is unsafe for highway driving. Secondly, we have increased I²R losses for the same power if our bus voltage is limited to such a low relative voltage. Furthermore, if we had an in-house inverter, it would allow us to add custom features, things like a cruise control loop or custom regenerative braking profiles. And this is something that we would want to implement in Helia. And finally, just as an organization, CUER is trying to disrupt the solar electric vehicle landscape, and the inverters present an excellent opportunity to do that through the use of wide bandgap materials, as I'll present. So when sizing the inverter, it was chosen to have an inverter rated for about 20 kilowatts at a bus voltage of 400 volts DC. Now, this figure was selected based on the fact that if one inverter fails, we still want to be able to drive the car, and we also want some overhead to perhaps scale up if we do increase the size of the vehicle in the future. And this corresponds to the switching devices needing to withstand 600 volts DC in the off state and about 60 amps continuous in the on state. So some of the devices that we considered, the first one was silicon MOSFETs, the cheapest and most widespread option. This has the benefit of being excellent in the switching performance aspect because it's a unipolar device, so we don't have this plasma to clear during the turnoff process. However, the on-state resistance is the main limitation of this device, and we can explore this using the classical silicon limit, which is based on a one-dimensional Poisson theory, which states that the drift region resistance, which tends to dominate the overall on-state resistance for a power MOSFET, is roughly proportional to the breakdown voltage to the power of 2.5. Now, it has been shown that this can be broken through devices like the super junction, and this can be illustrated in this curve here, where the blue line is the classical silicon limit, and we have devices such as the Infineon CoolMOS, which is a super junction device that then has decreased on-state resistance for the same blocking voltage that is predicted through the one-dimensional Poisson theory. So that was one device we considered, the classical silicon MOSFET. Still staying on silicon, we have the IGBTs, the insulated gate bipolar transistors. Now, these devices are a bipolar device, as suggested by the name, and because of that, we have this plasma built up in the on-state, which leads to conductivity modulation. And this significantly increases the on-state performance or decreases the on-state resistance of the device. However, the trade-off is now in the switching performance, as we then need to clear this plasma during the turnoff. And this slows down the device considerably compared to MOSFETs. And looking at devices, silicon IGBTs that fit that 600 volt, 60 amp range, I found that most of them tend to have an upper limit of about 20 to 50 kilohertz. And because of that limitation, I decided not to use silicon IGBTs for this inverter because I wasn't sure if I wanted to scale the switching frequency up even beyond that. So this is a good point to bring in the case for wide bandgap materials. So if we compare silicon carbide and gallium nitride using the Kang-Andrea figure of merit, which I'll show you in a minute, we can see that the wide bandgap materials offer orders of magnitude better performance in regards to on-state resistance and the breakdown voltage trade-off. And gallium nitride in particular is better for high frequency applications, and it is cheaper than silicon carbide given that we can grow it on a silicon substrate. So this last column here is comparing the figure of merit of silicon for each silicon carbide and GAN. And we can see that gallium nitride in particular offers vast improvements over standard silicon. And just visualizing the sort of physical properties of the three materials in this spiderweb chart, we can see that the blue line is silicon, and we have massive improvements in the high frequency and high voltage operation when we look at gallium nitride. So it was chosen to use gallium nitride, and specifically we chose to use the gallium nitride HEMT. Like the basic theory of this operation of this device is that we have this GAN heterojunction, and the lattice mismatch of these two layers creates a strain, which then leads to a piezoelectric effect. And then we have this piezopolarization effect where we have a two-dimensional electron gas at this heterojunction. And this structure on the right is actually a depletion mode HEMT, but what we want in our inverter is an enhancement mode device, which is then built by using a PGAN gate over here. The reason we want an enhancement mode device is that we want the device to be normally off, and then we want to turn it on rather than being the vice versa. And the specific device chosen was the GS66516 by GAN Systems. So in choosing GAN HEMTs, there were some massive challenges that we had to overcome, especially in the gate driving aspect of things. And the first one is that the gate voltage is extremely sensitive because the maximum gate voltage that GAN HEMTs can withstand is about 6 volts. And this is dangerously close to the threshold voltage to turn on the device. So we can see here this the recommended range is about 5 volts. And then if we have any overshoot of this gate source voltage, we can accidentally damage the device. So in order to prevent this from occurring, we have to critically damp or overdamp the LCR resonance circuit at the gate drive turn on loop. However, there's another challenge in that we actually may want some undershoot and ringing in the turn off. And I'll talk about why this might be beneficial. But this means that we have to have different damping ratios for the turn on and turn off loops. And illustrating the two loops here, we have the green turn on loop and the blue turn off loop. And these formula here are just showing that we want the turn on loop to be critically damped or overdamped, and the turn off loop to be underdamped. So the other gate driving challenge that we have is this parasitic Miller turn on effect. So if our CGS, the Miller capacitance, is charged above the threshold voltage during a high dV by dt event, we can accidentally turn on the device, which would then lead to a catastrophic failure of the inverter. So there are a couple of solutions to this. The first one is to add an alternate current path through a sink resistor. And the second solution actually is why we may want the underdamped turn off loop, as mentioned before. And that is if we, and this is looking specifically at a half bridge configuration where we have two complementary devices. If we adjust the dead time between the two devices such that we turn on the complementary switch just at the point where the gate source voltage of its other switch is at its minimum, we can then prevent this Miller turn on from occurring by ensuring that the overall gate source voltage stays below the threshold voltage. And that's why we may want this to actually go negative, so that if this stopped at 0, then this may increase above the threshold voltage. So one gate driver circuit that was proposed is this one here. And the top half is just setting up an isolated power supply. But this uses a standard MOSFET gate driver and a digital isolator to ensure there's isolation between the low voltage and high voltage sides of the device. And we can see that we have two resistors here. This bottom one is for the turn on loop, which is why it's a higher resistance than the turn off loop resistor over here. Another issue that we had to overcome is this issue of common source inductance. And basically, we can accidentally turn on the device by a large DI/dt event by biasing the source. And the main solution is to use a Kelvin connection to the source pin. So actually, the device chosen, the GS66516, has a dedicated Kelvin connection to the source over here. But if we had a device that didn't have it, we can construct one in the PCB layout, something like this. And this is the common source inductance. It's common to the gate source loop as well as the main power loop. And the other issue that we want to tackle is EMI shielding of the device and parasitic inductances. And there are three PCB layouts that are compared in this. The first one is known as lateral layout, this one over here, where all the components are placed on the top side. And we then have a shield layer underneath the top layer with the components. And this has the benefit of being a single layered design, which is beneficial if we want to keep the cost of constructing the PCB low, and also make sure that we can have a more simple design. But this also means that the EMI shielding properties of this device is proportional to the thickness of the overall board. We can sort of overcome this by considering a vertical layout where the main power loop goes through the PCB as such. And this actually provides EMI shielding by having a magnetic field self-cancellation between the opposing directions of current. And because this loop is a lot tighter than this loop, that effect is more pronounced in the vertical layout. However, we basically have, the first layout, the EMI shielding is not dependent on the thickness of the board, because you can have an internal layer sort of just over here that is blocking the EMI from the main power loop. In the second one, it does depend on the thickness of the board, because the current has to travel through the entire thickness of the board. And also we have components on the bottom side, which just makes the design a little bit harder to mount and heatsink. We can overcome this by combining the best of both worlds in this hybrid layout over here. And as you can see in the table, we basically take the best aspects of both designs. Now, stepping aside from the power stage of the inverter and looking at the control stage, the main way we control this is through field-oriented control. So we basically have a demand current set point in the rotor reference frame, so the direct and quadrature components of the motor current. And in our case, we actually set the quadrature component to 0, because that provides us maximum torque per amp of current. And the way this works is we basically take a current reading. We then transform the three phase currents into two axes using the Clark transform. And this is still in the stator reference frame. Then taking the rotor position into account, we can then transform this into the rotor reference frame. And then that gives us our measured direct and quadrature current, and we run that through a PID loop. And then we just transform it back and then send the signals to the inverter through some PWM modulation methods, such as sinusoidal PWM, or in our case, space vector modulation. So two different motor control platforms were compared. And the first one is this ST motor control SDK. And this is mainly chosen because it supports FOC, and also the rest of the vehicle is using ST as the basis for their microcontrollers. And this supports Hall effect current sensing over here in the phase current sensing, which is beneficial because then we have an isolated way of sensing the current. However, so I built up this little control stage board, and I found out that it was actually very difficult to configure this board on their software. It was possible, but it's not ideal for training new members of the CUER electrical team. And this is actually quite a big consideration when implementing anything new in the vehicle, is that we needed to be able to be easy for new members to use. And that led me to try out the other platform, which is the Infineon iMotion platform. This does not support Hall effect current sensing, which means we do have to use a shunt resistor and then figure out the isolation afterwards. However, the configuration process is much easier, and this is a trade-off that does need to be made for CUER. So the Infineon control stage, there are basically two options. The first one is in using something like the IMC 300, where the Infineon chip is just supplying the control algorithm, and then we then pass the signals out to an external gate driver and an external power stage. The other option is to use something like the IMD 110 series, where we have the gate driver integrated in the IC. And the good thing about the GS66516 transistor that was chosen is that it's perfectly compatible with a regular MOSFET gate driver. The output voltages do need to be adjusted, but that can be done using something like a Zener diode to clamp the output voltage. So this is sort of the recommended control stage topology. Now, given that actually, I did not have any lab access for this project. Most of it was done on PLECS to simulate the entire inverter, and the GS66516 devices did come with PLECS models that were used. So this is the whole inverter, and this consists of three simulations. The first one is the electrical simulation, which is the field-oriented control over here, and then the power stage. There is also a mechanical simulation to look at the output torque and speed characteristics, as well as a thermal model to look at the heat dissipation. So these are just some waveforms from the output. Going bottom to top, the bottom one is output speed of the motor. So this was set at a demand of 100 radians per second. The middle one is just simulating a load torque applied after some operation. And the top is the product of the two, which gives the output power. So this just showing that we have a working speed control loop, and it does respond reasonably to a load torque. And then these are some simulations of the output current, phase current, and phase voltage waveforms. Now, the main thing we got out of the simulation is that we can look at switching frequency and relate that to losses, and use that to determine what frequency we should switch the device at. So this is what we would expect from the device, where we have conduction losses relatively constant throughout, and switching losses increasing linearly with switching frequency. And we can see that the overall efficiency does not drop much between switching at 5 kilohertz and 25 kilohertz. And this 20 kilohertz mark is about where the switching and conduction losses are about the same. And that leads us to choose this as a recommended switching frequency. And this is at a cruising output power of 2.5 kilowatts. We can also look at power output and junction temperature, and the heatsink was sized as per the recommendations from GAN systems, which is about 1 joule per Kelvin thermal capacitance, and standard values for thermal resistance between the junction to case and case to ambient. And we can see that even at 6 kilowatts, which corresponds to the peak output of 12 kilowatts shared between two inverters, the junction temperature rises to about 45 degrees, which is still acceptable at an ambient of 25 degrees. So summing it all up, sorry, and this is the actual device. So I had these little half-bridge boards, but unfortunately, without access to labs, there was no way to actually construct the power stage and test it out with a real motor. But to conclude, the final recommendations from CUER that were gained from this project is, first of all, to use the Infineon control stage with the custom gate driver. So as mentioned before, this one here, where we have the custom gate driver instead of the integrated solution. And that was chosen so that we have full control over the turn on and turn off damping ratio. Also to use the hybrid PCB layout for EMI suppression, and selecting a switching frequency of about 20 kilohertz from based on the PLECS model. However, this figure does need to be validated experimentally, and I'm hoping to return to Cambridge once lockdown situations ease in Singapore, where I am, and actually construct this inverter. Finally, there's also a model of the transistor, the GS66516B, which is this one, which allows for bottom side cooling for the device. So these PCBs here are actually aluminum substrate ones, so we can have heat sinking done through the PCB and have a larger cold plate at the bottom. And this allows for having actually a double-sided heatsink design, which would save on the overall footprint of the device. Thank you.
Thank you very much. This is a very comprehensive overview of the projects and what has been achieved. And I can see is very much in the current interest how you can provide a power controller for large power, especially for electric vehicles. So in the interest of time, we could have one quick question if somebody would like to ask Rahul. No? So in this case, Rahul, thank you very much. That was a very nice talk.
Thank you.